We're doing lecture 16 on isomers. I'm Sarah Bluth, and let's just get right into it. So I have a few of these images, and I want you to think what they have in common. We can see here that there are obviously two different types of molecules, but they have some things in common. So here we have butane and isobutane. Over here there's 1, 2, 3, 4 carbons and 9, 10 hydrogens. And here we have exactly the same. We have 4 carbons and 10 hydrogens. Same thing over here. We have two different looking molecules, but they have the same components. And here as well. We've got these similar looking molecules, but they are different. So what are these called? They're called isomers. And what they are is a structure with the same chemicals, but different structures. So some of the ones that we saw are structural isomers or constitutional isomers, stereoisomers, enantiomers are these guys over here. And we're going to go over what exactly each of these terms mean over here. But these are just some examples of an isomer. So we're going to start with learning a little bit about organic chemistry, just to clear up some problems that could come up in later times. I know this confused me a lot at first. Organic chemistry, that's the study of carbon-containing compounds. It has usually carbons and hydrogens bound together by single or double bonds. So we take this image here, and that means something in chemistry. It looks kind of just like two little mountains or something, but that actually is a molecule. So that is this molecule right here, with all these carbons and hydrogens. So pretty much what this means is right here, I don't know if you can see that at all, if you can like see where I'm clicking, but this right here is a carbon, this right here is a carbon, here, here, here. And surrounding those carbons are hydrogens and bonds. So this is a carbon-carbon bond right here. And then to fill in that, what's that called? Because of the octet rule, we need to fill in the Lewis structure, right? So this carbon is bonded to 3 hydrogens, as you can see right here. Hydrogen, 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 then it goes to carbon, and then carbon, carbon, and these are surrounded by hydrogens as well on all sides. So we're going to see a lot of these kind of structures in this video, and just so you know what they are, sometimes you'll see something with like an OH over here, hydroxyl over here. That just means that instead of a hydrogen on this side, there's a hydroxyl, or anything else, really. Okay. So yeah, pretty much the lines are the bonds, the ends are the kinks or carbons, and then the hydrogens are implied. And we're going to assume that each carbon has 4 bonds. Oh. Okay, bear with me. Okay, so like we kind of talked about, there are multiple different types of isomers. I showed some examples earlier. These are all different types of isomers. So this is constitutional, we've got a cis and trans, and then an enantiomer. So what exactly do those words mean? Well, I have this little chart that kind of splits it up pretty nicely and evenly to be understood. So that first one I showed, constitutional isomers, those have the same sort of structure, but with small differences in position of a certain molecule. So this example right here is showing that this fluorine atom, Oh, sorry. Oh, yawn. Okay, this fluorine atom instead of being here is put over here. It does have the same number of atoms and everything. It is an isomer. It just has a different positioning of an atom. So there can be multiple types of constitutional isomers. There can be multiple ways that you arrange these atoms to make a different type of constitutional isomer. Anyway, that's pretty self-explanatory. Moving on to stereoisomers or spatial isomers. There are two types of these. We have let's start with diastereomers. These are isomers that have the same structure but are on one or the other side of a double carbon bond. So this is what we call cis and trans isomers. These carbons right here are double bonded to each other, and they have these other atoms branching off. So we have a cis isomer, which is an isomer with the same amount of the atoms on the same side. So these hydrogens are on the same side of the double bond. And then we have trans, which is the atoms on different sides or across from each other. So hydrogen here and hydrogen here. We'll go more into this. I'm kind of over-explaining right now, but we'll go more into that. Enantiomers, they are a type of stereoisomer that is a mirror image of itself. And we're going to cover a little bit more about that. Yeah, okay. Let's go. Okay, so more about constitutional isomers. There's more of these little shapes again for you guys, understanding that these are each carbons and hydrogens. So a constitutional isomer must have the same number of carbons and hydrogens. So this is the different types of constitutional isomers of hexane. And hexane we can see here has 1, 2, 3, 4, 5, 6 carbons that we can see. 1, 2, I don't know if you guys can see my mouse, so I'm just gonna click. 1, 2, 3, 4, 5, 6. And then implied are these hydrogens like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So hexane is a 6 carbon. Let's see if I can type this out. Carbon 6, and then hydrogen. Oh my gosh, now I'm forgetting how many it was. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 hydrogens. So if you want to find out if something is a constitutional isomer of hexane, you just need to look if it has the same amount of carbons and hydrogens. So, 1 second. Okay, so we know that these are, obviously, because they're all put together, but if we wanted to tell, we could just count the number of carbons. So let's see, in this 2-methylpentane, 1, 2, 3, 4, 5, 6 carbons, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogens, so it checks out. This is called 2-methylpentane because it is bonded onto the second carbon right here. Same thing as here, 1, 2, 3-methylpentane is connected to the third, and then 2 and 3 dimethylbutane is connected on the second and third carbon, and then dimethylbutane, it's 2 dimethylbutane is connected on the second carbon. It's 2 carbons connected onto the second carbon. So these are all isomers of each other. They're all the same type, the C6H12 hexane, but just different forms. So let's move on to the next one, which is stereoisomers. These are molecules with the same structural formula but with different arrangement of atoms in space. Okay, so what's the difference between that and what we were just talking about? Stereoisomers have a different spatial arrangement, and we're looking here at cis and trans isomers like we were talking about earlier. The structural formula for this one is CHCl, CHCl for both compounds. Oops. So these are, so we've got stereoisomers, diastereomers, It's tongue twister. And then these cis and trans isomers, so that's just an example of a diastereomer. Oh my gosh, that's a mouthful. So a cis isomer, oh, let's see if we can, well, okay, so yeah, there's two different types of diastereomers, which are the cis and trans, and then conformers. We're not going to really talk about conformers. I don't remember learning anything really about that in class. I don't think it'll be covered, or it wasn't covered in the test that we had. So yeah, we're not going to talk about that, but just focusing on the cis and trans, mostly for the diastereomers. Cis isomer is two like groups on the same side of a double carbon bond. We kind of talked about that. Trans isomer is two like groups on opposite sides of a double carbon bond. So if we were to look at this to identify the cis isomer, we just look for two of the same atoms on one side of the double carbon bond. So we've got on this side of the double carbon bond hydrogen, chlorine. Those are two different, so that's not a cis, that's going to be the trans. And then this over here, we got two hydrogens, two chlorines. They're on each other's side, the same side. Cis, the prefix cis means same, and then the prefix for trans means across. So you can see that these hydrogens are across from each other, these chlorines are across from each other. And that's how you can identify cis and trans. We kind of talked about that. So here's an example of a cis in one of those, or of a cis isomer and then a trans isomer, using that kind of, I'm not sure what this type of thing is called, but that kinked structure, like the organic molecule structure. That's an example of a cis isomer, and then here's one of trans. So something about this in real life is that cis unsaturated fats have lots of kinks in their lower density, and then saturated fats have no kinks and they stack better on each other. And then trans unsaturated fats, they don't have kinks, and the stacking is made a lot stronger by the double carbon bonds in neighboring chains interacting. So that's just kind of like a real world application. Cis, unsaturated fats, saturated fats, that's using these kind of bonds. Okay, so just kind of going over this again, what's the difference between the two main groups, constitutional and stereo, which were these two groups right here? The constitutional isomers are connected, not corrected, connected differently, and then stereoisomers are connected the same. And then, let's see, diastereomers versus enantiomers, which we're going to go into. Enantiomers are mirror images, diastereomers are not. So what is an enantiomer? Let's figure out. Enantiomers are what we call chiral objects. So here's a little example. We have a picture here of a left hand and a right hand in their mirror images of each other. And then when you put them on top of each other or superimpose them, they do not line up perfectly, so they can't be superimposed. For an example of an achiral object, we have a bottle here, and it's a mirror image of each other, but it can be superimposed, so it is not chiral. So molecule is chiral if the two mirror images are not superimposable in 3 dimensions. The word chiral actually is derived from the Greek word chir, I think it's pronounced, which means hand. And then this chirality most often occurs in molecules that contain a carbon that is attached to 4 different groups, which is what we call, oh my gosh, okay. Bear with me. Okay, that's an enantiomer, which is called a stereocenter. So we're going to figure out if a molecule is an enantiomer, if it's chiral, if it has a stereocenter. There we go. So what is a stereocenter? That is a carbon that is bonded to 4 different atoms or groups. And so, for example, here we have 2 stereocenters. So what makes this a stereocenter? It is bonded to different groups. So H3C over here, bromine, and then a carbon that, yeah, that is attached to, all three of these groups are completely different, so they're not the same. But if we were to say go over here to this carbon, I don't know if you can see that, it's connected to, I don't even know what CH3 is called, carbon high, yeah, carbon trihydrogen, I don't know. It's connected to these two CH3s, so these are two of the same things, and then a carbon, so that is not a stereocenter because it has a similar item it's connected to. Same here, carbon connected to carbon. Over here, it's connected to carbon, so not going to be a stereocenter. Moving on. Oh, also in a real life application is that many pharmaceuticals are chiral, and often only one enantiomer will be clinically active. So yeah, just kind of real world stuff. So let's practice this. We're gonna look at this molecule. I'm gonna try to do this right. I honestly, this will be good practice for me too. But we're gonna look at all these carbons and figure out if they are chiral or not. So we know automatically anything that looks like this carbon right here is attached to two hydrogens. And then also two carbons. So that's two pairs. So that is not going to be chiral. Same here, same here. Here, let's see, it's binded over here and over here to, I think those are trying to say carbons. And then carbon, carbon, that's not a stereocenter. What about here? So we've got a carbon connected to this long chain that has this pattern. And then we have it connected to a carbon here, but this carbon has this whole chain. So we're not just talking about the carbon, we're talking about what the carbon is connected to, like what chain it's connected to as well. So carbon, that goes like, okay, sorry, what was that? It's an alarm. Yeah. This, I believe, is a stereocenter, if I'm not mistaken, because it goes this way and connects to a different chain, and this way connects to a different chain. It's connected to a hydrogen here, and then it's connected to this carbon over here that's connected to this different chain. This one is a carbon chain going that way, a carbon chain going that way, this hydrogen, and then this carbon. I'm pretty sure this one's chiral as well. If I'm wrong, I'm so sorry. But I'm sure you guys will find better study guides. Anyway, this carbon, pretty sure that's stereocenter as well because it's connected to this long chain, to this chain, to this one, and then a hydrogen. So those are all different things. Something that kind of tripped me up was I was like, oh, it's connected to two carbons, so it can't be the same. So it won't be a chiral center. But it actually is because if this carbon, it's like taking into account not only the carbon, but what the carbon is attached to. Over here, that's two hydrogens. Double bonds never are going to be stereocenters, just keep that in mind. And then this is connected to a carbon, hydrogen, double bonded, so not going to be one. Two hydrogens over here, and then I think this one's a stereocenter as well. Yeah, so that is most of the stuff that I wanted to cover. I'm trying to think if there was anything else. Let me look over here. Kind of talked about all this. Oh, let's check if we got that right. This is the same exact thing. Okay, yeah. So the only one I forgot is this one right here. Because that one is connected to this hydroxyl, over here hydrogen, and then this carbon, and then this carbon chain. So this one has 5 stereocenters, making an enantiomer. This chart I also found to be really helpful. I didn't put this in my slides, but I like it. kind of goes over these constitutional isomers and different types. So these ones are like chain isomers, positional, functional, which we didn't really go into depth in ever, I don't think. But just know that these are all constitutional isomers. Enantiomers, these little guys, like if I stacked this guy onto this guy right here, they would not superimpose, kind of like that left hand, right hand thing, because this is the stereocenter right here. It's attached to this atom, this atom, this atom, and this atom, and they're all different. If, let's say, this is, okay, yeah, this is something I wanted to go over as well. Let's say this red kind of looking atom was, okay, let's say all these bottom ones were this yellow color. So this carbon was connected to 3 of the same thing and then a different thing up here. If we rotated this to be a mirror image of itself, it would still be the same. It would still be superimposable, which would make it non-chiral, which would make it wouldn't make it an enantiomer. It would just be the same exact molecule, but rotated a different way. Conformers we didn't really go over, and then cis and trans, if you can figure out which is the cis, which is the trans, is just looking at if it has 2 of the same molecules on the same side. I'm trying to go over more. I feel like this was a pretty like straightforward lecture, so I don't know if there's like a ton of material to necessarily go over. Let's see. Okay, we didn't really go over this. I'm gonna just totally jack Professor Mortensen's slide on this. So here we have kind of what we were talking about, those saturated and unsaturated fats. We have these hydrocarbon chains. Alkanes are all carbon single bonds. So this nice, just not straight because it's not straight, but this nice kinked line with no double bonds. Alkenes are 1 or more carbon bonds, which makes it unsaturated, kind of like we were talking about those unsaturated fats. You're going to see this in like lipids. It'll have like a hydrophilic, or what am I saying? Yeah, hydrophilic head, like a phosphate head over here, and then a hydrophobic tail, which is just like a tail of hydrocarbon chains. So that's kind of what like fats are made out of, which is why it's showing this lard, this saturated hydrocarbon, very bad for you. Unsaturated has those double bonds. Alkynes are 1 or more triple carbon bond, and that's an unsaturated hydrocarbon as well as alkenes, but it has that triple bond. Oh, okay. So that's kind of like a real life application. Let's see if there's any other material we can go over. Sorry, this is kind of out of order, but yeah, I think that's pretty much everything. I would say ask me a question, but you can't. So thanks so much for watching, and I hope you learned something from this. Thank you.